Okay guys, so in this small tutorial video, we're going to talk about derive the period of a physical pendulum, right? That is the full derivation we want to do it here today. So the physical pendulum, when we talk about, it's like any irregular shape object you have. Let's draw it out. So let's say this is an irregular shape body, which has a point P right here, through which the whole rotational body is going to be doing a simple harmonic motion, doing back and forth motion. Okay, so we have an irregular shape body pivoted from rotational axis point P. Okay, and it forms angle theta from the equilibrium, and then you let go, so it will go back and forth moment. So this point P is actually distance r away from the center of mass. Let's say this is the center of mass right here of this body. It has a weight going down. Let's say this is capital MG. This M doesn't look like M. Let's draw it properly. So this is MG. And of course that the restoring force, as a simple pendulum, it is also going to be the mg sine theta. And in this case, it is doing this, doing back and forth motion around the rotational axis like that. So you have a restoring force going this direction, and we call this component of the weight as a mg sine theta. You say, where is theta here? Well, the theta is forming the angle right there, right? So this is theta right there. And as I said in the earlier, that you are moving your physical pendulum theta rotational distance away and from equilibrium, and then let go, so that it will go back and forth motion of that too. So this is your this is the equilibrium position, and you move, that is the angle theta as well. Cool. This has, if you want me to draw it, I can draw it mg cosine theta right here as well. Okay, so same as a simple harmonic motion too, here is also going to be a period t that we want to derive it. Here the center of mass is r distance away from the rotational axis. Okay, so if we were to draw or derive using a torque, because this is a physical pendulum, it's going back and forth, I could say that the restoring force, which is causing restoring torque, which is causing it to go back and forth, I can write that as a summation of all torque equals to I alpha. Okay, and now that is the force, which is mg sine theta times r. So mg sine theta times r would make the official torque responsible for it to go back and forth. Right here, the negative sign shows that the restoring torque is a clockwise and the displacement is a counterclockwise. You remember F equals to negative kx? Remember F equals to negative kx. This is a similar kind of situation too, that you have a negative sign that shows that the restoring force is the opposite direction of the displacement. Same thing is happening here too. So if we rearrange this equation, what we will get? Well, let's see if we do this way. I alpha negative mg r sine theta. We consider that alpha as a d square theta dt square. That's a second order differential equation for the angular displacement. Then I can have your mg r sine theta over I. Guys, I gave you this. This is a second order differential equation for the angular displacement, which is going to give you the period for the physical pendulum. Now, as we always do, small angle approximation. So using a small angle approximation, what we can write, that the sine theta value is very, very close to theta. So we can replace sine theta as just theta, right? And if we do that, what we're going to get? We're going to get d squared theta over dt squared, and only thing's going to left is mgr over I, and that is of theta. This equation is very much analogous to the simple harmonic motion equation, which we have derived earlier too, which was d squared x over dt squared negative omega square x. Look, x replaced by theta, d squared x by dt squared replaced by d squared theta, dt squared. That means your omega square you can compare with the mgr I. So here in this side, I'll write your omega square is nothing but mgr over I. I is moment of inertia. Okay. So if we have that, can I write that the omega is a square root of a mgr over I? I can write that. Also, I do know that the omega is equals to 2 pi over t, and which is indeed equals to your mgr over I. So I can rearrange the equation, and now finally I have the equation for the period of a physical pendulum, not a simple harmonic pendulum. It's a physical pendulum. Its entire body with the center of mass moving back and forth. And what kind of period equation you can give for that? Here you go. You can have that rearranged from this, and we got mgr, right? So t equals to 2 pi square root I over mgr. This is the period for a physical pendulum. Period of a physical pendulum. So quickly, what is the difference between the simple harmonic motion, simple harmonic pendulum, or a simple pendulum rather, versus a physical pendulum? Is that in a simple pendulum you treat the object as just a point. Here you are treating the whole body as a physical body, which is moving back and forth with the torque as a mgr sine theta as a restoring force. And hence, instead of t equals to 2 pi, m over k, we are getting I over mgr. Okay, I hope that helps. Thank you.